Hi everyone, I'm Deepak. I'm a final year PhD student at Stanford. I'm advised by Matej Arya, and I'm excited today to talk about work that I've been doing at NVIDIA to train large-scale language models on GPU clusters. Machine learning has powered state-of-the-art results across a broad range of applications. As the amount of available compute and training data has increased, so too has the size of machine learning models. This graph shows us the sizes of state-of-the-art models used in natural language processing. Over the last 3 or so years, the number of parameters in these models have increased by more than 3 orders of magnitude, drastically increasing the number of compute operations needed to train these models as well. In this work, we discuss various techniques needed to train models with up to 1 trillion parameters, which far exceed the memory capacity of single GPUs in reasonable timeframes. Using a combination of various techniques, we were able to efficiently run training iterations for GPT models with up to 1 trillion parameters using 3,000 plus A100 GPUs with extremely graceful scaling. With this high throughput, we estimate that we will be able to train a model with trillion parameters end-to-end in about 3 months using 3,072 A100 GPUs. Our results are a byproduct of optimized hardware with state-of-the-art GPUs and high bandwidth interconnects between GPUs on the same and different servers. A hybrid parallelization scheme that minimizes the amount of communication across GPUs while still keeping devices busy, and various domain-specific optimizations to target both computation and communication. Our code is open source on GitHub, and we would love for you to check it out. First, I'm going to describe the hardware setup on which we obtain these results. We ran experiments on Selene, a GPU cluster with A100 GPUs. Each A100 GPU can sustain a peak device throughput of 312 teraflops per second. GPUs within a cluster node are connected by NVLink and NVSwitch, and GPUs across cluster nodes are connected by 200 gigabits per second InfiniBand cards. In aggregate, Selene is able to provide 2.8 exaflops of peak AI performance. It turns out that even such an optimized hardware setup is not sufficient to scale to large models. In particular, the model training graph needs to be distributed among the training resources in a clever way in order to make sure that the amount of communication being performed across devices does not overwhelm end-to-end computation time. Training a deep neural network model at a high level involves finding weight parameters W that fit a training data set, consisting often of inputs and associated labels. A forward pass through the model generates intermediate activations as well as a prediction. These predictions could be incorrect. In this particular instance, we predicted that this picture of a tiger is actually a lion. Errors between the predictions and the true labels are backpropagated through the model in a backward pass, generating weight gradients that are then used to update the model's parameters. The backward pass uses both the weight parameters and intermediate activations as inputs in order to compute the weight gradients. This optimization procedure is performed in iterations, and each iteration can be parallelized within a GPU as well as across GPUs. Each iteration of model training can be distributed across multiple GPUs in various ways. For example, the common way of distributing model training for models that fit on a single worker is to use a paradigm called data parallelism. With data parallelism, every worker has a copy of the model. The input data set is sharded, and each worker generates a weight gradient on its subset of the data completely independently. At the end of every iteration, workers aggregate the weight gradients across the different workers in order to make sure that every worker sees a consistent version of the weights. Another way to parallelize model training is to use model parallelism, which is typically a technique used to train models that are larger than the memory capacity of a single GPU. The model parameters can be split over the available workers or devices in multiple ways. For example, in tensor model parallelism, each operator or layer in the model can be split over the available workers or devices. With interlayer model parallelism, on the other hand, we assign each layer or operator to different workers. In this particular example, layers 1 and 2 are assigned to worker 1, and layers 3 and 4 are assigned to worker 2. Depending on how the model training graph is split over the available devices, different communication patterns are needed. For example, with data parallelism, we need to perform all-to-all communication of the weight gradients in order to make sure that every worker sees a consistent version of the weight parameters. With tensor model parallelism, we need to perform all-to-all communication of the partial activations and gradients generated on each worker. And with interlayer model parallelism, we need to perform point-to-point communication of the intermediate activations and gradients generated on each layer subset. The upshot of all of this is that certain types of parallelism methods require collective communication, such as data parallelism and tensor model parallelism, while other methods of parallelism, such as interlayer model parallelism, can get away with much cheaper point-to-point communication. As it turns out, communication is not the only axis of interest that we should compare along to reason about performance of distributed training schemes. Even though interlayer model parallelism can drastically reduce the amount of inter-device communication, it can also lead to device idle periods as devices wait for inputs to propagate through the devices, consequently limiting throughput. In this timeline diagram, I'm showing per device utilization with time on the x-axis. Blue boxes show forward passes, green boxes show backward passes, and the numbers in each box indicate unique identifiers given to particular inputs. We see that the backward pass for input 1 can be initiated only after the forward pass for input 1 completely runs through devices 1 through 4. We observe that large parts of the timeline diagram are gray, indicating idle periods. This poor resource utilization leads to low throughput. Pipelining is an idea that has been proposed by recent work like Pipedream and gpipe to address this issue. A batch of inputs is split into smaller microbatches, and execution is then pipelined across these microbatches. In this particular example, I'm splitting a batch consisting of 4 samples into 4 microbatches. Device 1 no longer has to wait for the forward and backward pass of microbatch 1 to complete before starting on the forward pass of microbatch 2. Execution for microbatch 2 thus can be started as soon as the forward pass for microbatch 1 is completed. The optimizer can be step and weight parameters updated when all microbatches in a batch are completed. Note that every device is idle for a couple of time units at the start and end of a batch. We call this a pipeline flush, as devices wait for inputs to either be injected into the pipeline or then subsequently drained out at the end of a batch. We can now exactly quantify the amount of time different devices spend idling. We call this the pipeline bubble, and it's equal to P-1 forward passes and P-1 backward passes, where P is the depth of the pipeline. In this particular example, P is equal to 4. The reason why the pipeline bubble is equal to P-1 forward passes and P-1 backward passes is because microbatches first need to be injected into a pipeline and then drained. If T sub F is the time taken for the forward pass of a single microbatch, and T sub B is the time taken for the backward pass of a single microbatch, then if a batch has M microbatches, the ideal amount of time taken by these M microbatches is just going to be M times TF plus TB. The total time spent in the pipeline bubble is going to be P-1 times TF plus TB. And thus the fraction of ideal total time that's spent in a pipeline bubble is just going to be the ratio of those two quantities, which is equal to P-1 divided by M. Thus, we see that at large batch sizes, where M, or the total number of microbatches in a batch, is large, then the fraction of ideal time spent in the pipeline bubble is going to be small. We can see these results in action. I'm going to show the results of a weak scaling experiment where the size of the model is going to be proportionally increased as the pipeline parallel size increases. I'm going to show results for two different batch sizes. The y-axis shows per GPU achieved throughput. If we have perfect linear scaling, we would expect this line to stay pretty flat, horizontal, and parallel to the x-axis. We see that as we increase the size of a GPT model from 16.2 billion parameters to 122 billion parameters, the throughput per GPU decreases. We see that this decrease in throughput is particularly stark for a small batch size where the effect of the pipeline bubble is much more pronounced. On the other hand, we see that for the larger batch size of 128, throughput remains fairly flat, indicating that pipeline parallelism scales fairly well. We thus see that different modes of model parallelism have different trade-offs. While tensor model parallelism features expensive collective communication, pipeline model parallelism features much cheaper point-to-point communication. Tensor parallelism, on the other hand, always keeps devices active, whereas pipeline parallelism can result in device idle periods or pipeline bubble events. These trade-offs get much more complicated when we want to compose tensor and pipeline model parallelism. Additionally, we can add data parallelism into the mix, and this yields yet more trade-offs. It turns out that we can schedule the forward and backward passes of various microbatches, as well as the computations corresponding to different layers in other ways as well, leading to other trade-offs. In particular here, we can split a model into a larger number of stages than we have devices. So instead of mapping a model into 4 stages and then housing those 4 stages on 4 different devices, we can instead split a model into 8 stages and then map those 8 stages to 4 devices in an interleave fashion. In the timeline diagram at the bottom of this slide, we show such an interleave scheme. The dark colors show the first stage on the particular device, and the light colors show the second stage. Blue, as before, shows forward passes, while green shows backward passes. We see that with this interleave scheme, the total amount of time spent in idle periods at the start and end of the batch is much smaller. This is because the total amount of time spent in the forward and backward pass for each stage is now cut in half. Consequently, the pipeline bubble size is also reduced in size by 2x. However, we see that this interleave schedule does not come for free. Since now every device has 2 stages, and control needs to pass through these 2 stages at different points in time, the amount of communication needed with this interleave schedule is also going to be doubled. And thus we see that this new interleave schedule presents a trade-off. While it reduces the pipeline bubble size, it also increases the amount of communication. We can now quantitatively see the impact of this interleave schedule. As before, I'm showing per GPU throughput on the y-axis. On the x-axis now, I'm showing the batch size. All throughputs are shown for a 175 billion parameter model using 96 A100 GPUs. We see that at small batch sizes, where the regular non-interleave schedule suffers from large pipeline bubble sizes, the non-interleave schedule improves throughput by as much as 1.5x. Now we see that as we increase the batch size, the impact of the pipeline bubble for the vanilla non-interleave schedule decreases, and thus the gap between the 2 schedules is closed. We thus see that this configuration space of degrees of pipeline tensor and data parallelism, as well as the pipeline schedule, can greatly impact the amount of communication, the size of the pipeline bubble, the memory footprint, and consequently the performance of distributed configurations that we see in practice. Other hyperparameters such as the global batch size, as well as the micro batch size, also greatly impact the performance we observe. For more details on what the various trade-offs are for these different configuration parameters, please look at our preprint on arXiv. Finally, we found that we also needed to implement various domain-specific optimizations to target both the computation and communication pipelines of our distributed implementation. To obtain good performance on the latest hardware, we found that we needed to optimize the computation graph by manually fusing certain memory-bound kernels, as well as using PyTorch's JIT functionality to reduce the number of memory accesses in an automated fashion for various operators in our model training graph. We also found that when composing pipeline and tensor model parallelism, certain types of communication proved to be redundant, and we can implement an optimization that we call the scatter-gather optimization to reduce the number of bytes that need to be sent between devices on different servers. As before, I'm going to show per GPU throughput on the y-axis and batch size on the x-axis. This is going to be for the GPT-3 model with 175 billion parameters using 96 A100 GPUs. We see that across the spectrum of batch sizes, the scatter-gather communication optimization can improve throughput by between 10 to 15%. Our implementation is built on top of the Megatron training system for transformer-based language models. Our implementation is built on top of PyTorch and supports various transformer-based models like GPT and BERT. While a lot of the experiments that we presented in this talk were on large GPT models, we found that we were able to obtain good performance on a large number of smaller models as well. For example, BERT base and BERT large, as well as GPT-2. Our implementation also obtained good performance at small scale factors using small number of GPUs. Our implementation supports different types of model parallelism, such as tensor and pipeline model parallelism, as well as data parallelism, and different types of precision as well. For example, FP16 as well as FP32. Our repository's main README file has instructions on how to train these models, and the main driver files are pre-trained GPT.py and pre-trained BERT.py. With that, I want to conclude. In this talk, I showed how we can compose pipeline and tensor model parallelism with data parallelism to train transformer models with up to 1 trillion parameters at scale with thousands of GPUs with extremely high efficiency. The net aggregate throughput of our training was 502 petaflops per second, which is 52% of theoretical peak. We have a preprint discussing these various insights as well as more experiments on arXiv, and I encourage you to check that out. With that, I'm happy to answer questions.